Early on in the COVID-19 epidemic, people were throwing around the word exponential a whole lot. In this video, we're going to examine a key feature of exponential growth and learn why, even though the epidemic curve seems exponential at the beginning, it really isn't, and why that's a very good thing. We will be focusing on one key number, doubling time. We will introduce the concept with exponential functions, learn how to apply it to other functions, and then look at its significance in interpreting the COVID-19 data that is coming in. We'll introduce the concept of doubling time using a simple example from finance. Suppose we are given P0 dollars or euro or rupee, and we can invest it into an account yielding 3% compound interest. We start at time 0, and we want that P of t equals 2 times P of 0. So we start with the equation P of t equals P0 times 1 plus I to the t, because we're dealing with compound interest, so 1 plus I to the t is the accumulation factor. We first substitute 0 and obtain P of 0 is equal to P0. The next thing we do is we substitute our interest rate in, and we obtain 2 times P0 equals P0 times 1.03 to the t. And we see, solving for t, that we get t equals log base 1.03 of 2. And that will be how long it takes for us to double our money. So I've gone over to Desmos and I've graphed the equation, P0 times 1.03 to the t. And what I want to bring your attention to is down here, the doubling time is also going to be the difference between the x coordinates, x1 and x0 right over here, and I've put it on the x-axis. I have a projection, and you note that it is of course equal to what we just calculated, log base 1.03 of 2. And what I'll bring your attention to now is watch what happens to the doubling time as I just change only the initial investment. You notice it stays exactly the same. So let's generalize now for our percent compound interest, again starting at time 0. We want to double our money. We set up the formula as before, and we see, solving 2P0 equals P0 times 1 plus R to the t, we get that the time to double is going to be log base 1 plus R of 2. So in Excel, I've gone ahead and calculated the time to double for various interest rates from 2% up until 7%. And we see that at 2% it takes 35 years to double the money, whereas at 7% higher interest rate, of course, it takes a lot less time, about 10 years or so. And it's just worth pointing out now that there's a nice little rule called the rule of 72, which allows for a quick calculation of doubling time in finance. And it works as follows, and you can extract it from the log rules that we just saw a little bit earlier, that the time to double is going to be approximately 72 divided by R, where R is the compound interest rate. And we see it right here that if we just took 72 divided by 2, we would have had 36 years to double our money, and it's pretty close to what we got as 35, and so on up until around 10 years, very close over here as well. Now what we're going to do is, leaving the initial investment at 1, because we saw that it doesn't make a difference in the doubling time, I'm going to adjust the interest rate, and let's see the doubling time change. I'll scroll down a little so you can see it. And we notice, as expected, as we increase our interest rate, here we have 4%, using the rule of 72. 72 divided by 4 would be 18, so here it is, 17.7 years to double the money. Moving further, we see that the doubling time, of course, shrinks. So the higher the interest rate, the less time it takes to double our money. Let's now consider the case of continuous growth, or if it's for finance, continuous compounding. We'll start again at time 0, and we want to double our money this time, or double the population. We set up the formula, P of t equals P0 e to the RT, and the formula is a bit different for compounding continuously, or continuous growth. Once again, though, we obtain that P of 0 is equal to P0, that is our starting population. We get that 2P0 is equal to P0 e to the RT. The P0's cancel, and we see that t is equal to natural log of 2 divided by r, where r is the growth factor. That will be our time to double. But let's say we wanted to start not just at time equals 0 and double our money or double the population, but at any time t naught. And we'll have a population or amount of money, p of t naught, and we want to double it to 2 times p of t naught. And the question is, how long will it take to double? So we set up the equation using the continuous compounding or continuous growth model, and we see that we get 2 p naught e to the r t naught equals p naught e to the rt. And we want to solve that. So very simply, the p naughts will cancel on both sides. And we can move the e over to the other side, and we get 2 equals e to the rt over e to the rt naught. Using just the basic laws of exponents, we see that we get 2 equals e to the r t minus t naught. And solving, we get t minus t naught is equal to the natural log of 2 over r, where r is going to be the growth rate. That is going to be our time to double. So we notice something really important here is that this is a constant. This does not change. It's a constant, and it has no variable t in it, which is really important. It will be the same anywhere along the curve. Moving over to Desmos, I've graphed p naught e to the rt. And again, on the floor, so to speak, on the x-axis, you see a projection of the difference between the initial and double, so that way we can have the doubling time. And I see here that the doubling time, which is the same as x1 minus x0, is of course ln of 2 over r, as we expected. And as before, what I'm going to do is just play around with p naught, and you'll see, as before, the doubling time does not change even if our initial population changes. By starting at t equals 0, this is always going to stay the same. So let's now adjust the initial point, x0, which would have been t0, and see what happens to the doubling time. Again, the doubling time is down here. It's 13.86. Watch what happens. If I move along, it stays constant. That is something very unique to exponential curves. And this is what p naught e to the rt. We can just show that it's true also in the example from earlier. Watch what happens. Same thing. It's on the bottom. It's 14.2. No matter where I move that point to, that initial point, the time to double stays constant. We'll see a situation where that is not the case in just a moment. In the first video, in the Dovid versus COVID series, one of the examples we used was the logistic model. That time we actually included a threshold, but let's keep things a bit simpler this time. We'll look at a logistic function with no threshold, the classic logistic function. We see on the right the corresponding integral curve for a particular initial condition. Now we're actually going to derive this equation in just a bit to understand how logistic growth is, in fact, different from exponential growth. And although the COVID-19 models are not logistic either, they do share a particular feature with regard to variable doubling times, as we'll see in just a moment. Before deriving the logistic function, we return to exponential growth to understand where the differences in the two growths actually come from. Back in 1798, an economist by the name of Malthus published a paper in which he observed that the rate of a population's growth is proportional to the size of the population. And from that we have the equation dp dt equals rp, where r is the intrinsic growth rate. Now this is a differential equation. So we can solve it by separating, moving the p over to the left-hand side, and then taking the integral. So we take the integral of dp over p is equal to the integral of r dt. That gives us that the natural log of p is equal to rt plus c, where c is some constant of integration. Solving, we get the general solution, which is that the population at time t is equal to c e to the rt. And in the very first video, we saw that that would yield infinitely many solutions, and we could look at them on the graph as integral curves. If we set t equal to 0, we get p of 0 equals c, and we call that the initial population. And then we can have an initial value problem and look at a particular solution. And that solution is going to be p of t equals p naught e to the rt, as we've already been playing around with. But it's important to recognize that that was the solution to the differential equation you see here on the right, dp dt, equals RP, which came from the very straightforward hypothesis of Malthus. So congratulations, you just solved your first differential equation, or watched someone solve one. Let's move on to another one. We changed the hypothesis a bit. We're going to keep the first hypothesis, Malthus is true, for small population sizes, so that with a small population, the rate of a population's growth is proportional to the size of the population, but as the population grows, we're going to limit it. And we represent that here by changing the differential equation as follows. We say that dp dt, the change in the population with respect to time, is now going to equal r minus ap times p. So we've replaced r with r minus ap, where a is some limiting factor. So that as the population grows, the actual curve will change. We'll see that in a little bit. But for small populations, this is roughly equal to just rp, as in the first hypothesis. We're going to let k equal r over a, and we're going to see the significance of k in the final version, in the solution. It's going to be the carrying capacity. So we rewrite as follows. The differential equation becomes dp dt equals r times 1 minus p over k times p. Now this is a separable equation, so we bring everything with p in it over to the left-hand side. And we integrate. Before we do so, I'm going to decompose this fraction. And if you're not familiar with partial fraction decomposition, you can just check that this line over here is true by combining these two fractions, and you will once again get 1 over 1 minus p over k times p. I can now integrate, and when I do so, and applying the laws of logarithms, I obtain that the natural log of p over 1 minus p over k is equal to rt plus c, where c is a constant of integration. Solving, I see the general solution here on the screen. And what I need to do next is solve for c. So I substitute t equals 0. By substituting t equals 0, I have p naught over 1 minus p naught over k. And it's going to take a little bit of algebra, and I'm not going to bother going through all of the steps now. But when I solve for p, this is the solution that I obtained. Now, remember, this is the solution to the differential equation you see here on the right. And when we graph this for any particular p naught, what we get is the logistic function. And it's worth noting that the small change that we made to the differential equation from r times p to r minus ap times p yielded a drastically different equation. So I've gone ahead and I've graphed the logistic function that we just derived a moment ago. And on the screen, what you see is a particular solution for the case where the initial population is 0.007. And this I've scaled down so that way the carrying capacity is 1. And what you see over here is it does seem to be relatively exponential at the beginning, and that's not far from the truth. It really is close. But it goes through this inflection point over here and changes concavity. It goes from being convex to concave, and that's going to have an interesting effect on the doubling time, and we'll see that now. So just like we did earlier when we calculated the doubling time anywhere on an exponential curve, we're now going to do the same to find what is the doubling time anywhere on a logistic curve, which means we want to find t such that p of t is equal to 2 times p of t naught, the population at another time, for any time t naught. And that means the time to double will then be t minus t naught. So we begin. We take our equation that you see here, and we double it. So we say 2 times p of t naught for some particular value is equal to p naught k over p naught plus k minus p naught times e to the negative rt. And this t here, this is the key piece of the equation, because that's what we want to isolate. That's what we want to find. So I've shown a few of the steps, not all of them. And we isolate, we get e to the negative rt all by itself, and then we can take the natural logarithm of both sides, and we clean it up. Now, I didn't do a great job of cleaning it up, and I stopped at a certain point because you'll see that I've pulled out the natural log of 2 over r, and we still have a whole big mess of stuff left over here in our doubling time. And you could probably clean it up a little bit further, by all means, please do. But it's not necessary, because what we notice is something really interesting. We notice that this is no longer a constant doubling time, but a variable doubling time, that this is going to vary depending on t naught, as a matter of fact, whereas in the exponential function case, our doubling time did not vary. It was constant. So let's take a look now at the curve and see that in action. We return now to the logistic curve that we graphed just a moment ago, and this time I've included an initial and double point on the curve, and also on the x-axis there's a projection, and that's going to represent the doubling time, and it's going to be the difference between the x-coordinates of the initial point and the double point. And I want to bring your attention to that because as I move along the curve, I'll do it slowly, watch what happens. It's very subtle at first, but if you look at the x-axis, I know it's tempting to look at the red and green dots, don't. Look at the x-axis. You'll notice it's growing. So I'll do it again, I'll return back to the beginning. And this time, either look at the x-axis or look over here, where it says t equals x1 minus x0. And you'll notice that as I move along the curve, the beginning doesn't change much, but as I get closer and closer and closer to that inflection point, the doubling time grows. And in fact, in this model, because you can't double once you're beyond the inflection point, you can't go beyond the carrying capacity, it's not even defined beyond that, but we do see that it grows. Back to the beginning one more time, you'll notice that I've also included natural log of 2 over r, which is the doubling time for exponential, and you do see that it is relatively close at the beginning, and it stays close for a bit. And it's only after a little bit of time that it starts to veer off and grow. Now this is a very good thing because our models, that we'll see in just a moment for COVID-19, even though they're not actually logistic, they do have this feature in common, that as we move along, we're going to see the doubling time growing. It moves away from exponential and becomes more closely related to logistic here. What I've done also is I've included another graph down below, and this represents doubling time as a function of time. Now I've scaled it down. I've just divided by 100 so it fits on the same graph right here. So if you just multiply this by 100, you would of course get 8.9, which means that at 21, if I move along and I was at 21 right here, day 21, what I would have is, it's close to, yeah, perfect, got it, 8.89, which I see on this curve we saw just a moment ago, was how long it would take to double starting at this point. How long would it take to reach the double population? And we're now ready to move to raw data for the COVID-19 epidemic and see how we can look at the doubling time and what it will tell us about our position on the curve. So we finally found the number that we want to grow, this doubling time number. It's time to apply it to the SEIR model that we developed last time. But before we do so, I need to extract the infected fraction that you see here. And I've pulled it out from the others, the susceptible, the infectious, and the recovered. And then I'm going to look at the cumulative infected fraction. And the reason for doing that is because this is the data that's coming in. So now that we have this, we know what we're looking at. It is not actually logistic, but it has some features that are similar to a logistic model. Let's look at the raw data now. I've chosen South Korea, Italy, and the US because they are at different places in the epidemic. In the top row, you see the cumulative confirmed cases as well as deaths. We're going to focus on the cumulative cases, but looking at doubling time for deaths is also valid. Now, in the bottom row, we have the doubling time for those confirmed cases. We notice that although it doesn't appear, the doubling time at the beginning is very low in all of these cases. Let's focus now on South Korea. Moving along, we see that the doubling time started to grow. And now this was clearly related to the position in the curve. Now, as South Korea moved through the epidemic, nearing and eventually passing the inflection point, the doubling time really took off. Let's look now at Italy. Clearly, the epidemic isn't over. We haven't rounded out the S in our curve. But look at the doubling time. It's really trending upward now. It's starting to move. This is good news. Look at the US. Over here in the US, well, not over here, I'm actually filming this in Italy, over there in the US, we can see that the doubling time is still constant. And the reason for that is that they're still early on in the curve, so it's roughly exponential. But this makes sense. They're a couple of weeks behind Italy. The good news, however, is that the x-axis in all of these cases is time. South Korea is pretty much there. Italy will get there. We're closer. The US will get there. France will get there. The world will get there. Looking at the news can be excruciating. Hearing the stories, reading the graphs makes me cringe on a daily basis. But we have one number that we want to increase. And as soon as that doubling time is really large, it's safe to say that this epidemic will be effectively over.